Hello, everyone. Welcome to our third ACT session. As usual, it's me, Hasith, and today we're just going to pick up where we left off. So, one second as I move some things around. Okay. So, last time we talked about creating quadratics, and that got a little bit complicated, admittedly. So today we're going to start with something new from scratch that I actually think might be a little bit easier, even if it initially seems complicated. So we're not going to do a mini quiz right now. Don't worry. I don't feel like starting you guys off with that. Um, Today, we're going to start off with exponential models. So let's read this question. A researcher estimates that the population in a city is increasing at an annual rate of 0.6%. If the current population of the city is 80,000, which of the following expressions appropriately models the population of the city T years from now? So I just wanted to say a lot of questions are going to have this question type, which is which of the following expressions appropriately models the whatever. Basically, all that means is what equation is the right equation. So just you have to create an equation and then select the correct equation from the answer choices. So, okay, in this case, this equation type is going to be what we call an exponential model. And I'll show you the exponential model looks like this. Y is equal to A times B to the power of X, where A is the starting point, and then B is the growth slash decay factor, and then X is the change. And this could be anything. It could be time, it could be the amount of something, anything really. So let me explain what each of these terms mean. So the first term, A, which is going to be start, that represents, well, your starting point, how much of something you initially have. So in this case, Y is going to be the final amount of something, and then A is going to be the starting amount. So in this case, it says if the current population of the city is 80,000, so current population 80,000, that is going to be our start. So let's begin building our exponential equation. So Y is equal to 80,000. Yep. All right, 1 second. I'm trying to adjust this. Okay. All right, and then next we have our growth factor. So our growth factor is, our growth or decay factor is going to be a type of percentage where I want you guys to imagine this. If you don't know a lot about percentages, then pay attention. 1.00. This is considered 100%. This is considered the full amount of something, okay? Anything less than 1.0 is going to be something below 100%. And then likewise, anything greater than 1.00 is going to be more than 100%. And good thing is that we can model change this way. So they say this population of the city is increasing at a rate of 0.6%. So in order to model 0.6%, 0.6%, that's written as 0.006, where this might be a little bit confusing, but I'll give another example. If you had 12%, it would be represented as 0.12. And then whether or not it's going to be an increasing or decreasing factor, you add this value to 1.0 and you get how much your population is growing by. So in this case, B is equal to 1.00 plus 0.006, which is simply 1.006. Another way you can write that is, well, simply, like they have in this equation, 1 plus 0.006. So on the model, we can do what they did, 1 plus 0.006. And then we have our growth factor, sorry, not growth factor, our change. And the change is going to be what your X is typically. You know, when you're plugging things in, when it's like, oh, at point X, what is Y? That is what your change is going to be. So in this case, the X variable that we're changing is going to be T. So T is going to be at the top there. So this is our final equation. And which of the following choices matches at best? Okay, so we have C over here. This is not a good, this is not the correct answer because, well, it's obviously not identical to our answer, but I'll explain why this is incorrect. You see, remember, the population is growing, right? So the growth is based off of the initial population, where if you have a small amount of population, like 100, and it keeps on growing, it's going to be less overall growth than if you had a population of 1,000, and then it's grew at like the same percentage. So in order to do that, you need to have the growth, the area that represents growth, it has to be directly tied to the starting value. This is separate from that because it's adding, not multiplying. So therefore, it's not going to take the 80,000 into account. It's going to represent very, very small growth. Now, D, this is the one where a lot of people get tripped up, where they initially get something right, which is that 0.6% is equal to 0.006, but they put that as the growth factor. The problem with this is that 0.006 is going to severely decrease your population, not increase your population. Remember, if something is increasing, then its growth factor is going to be above 1. If it's decreasing, then its growth factor is going to be below 1. And clearly that makes sense here because 1 plus 0.006, it's above 1, representing growth. A and B are very similar, except the difference is that the T is on the outside for A and the T is on the inside for B. A is going to be the correct option. The T needs to be on the outside. The T can't be on the inside because remember, this T, it's supposed to take all of this into account, where it's saying, okay, this is the original value, this is how much we're increasing it by. If you do just T, it's only going to acknowledge the 0.006%, and it's not going to acknowledge the facts that, oh, we started with the full population, right? So that's why A is the correct answer. So this is another question where they give you a table and they give you data and they ask you to function and make a model off of that. So, okay, let's see. The table above gives the initial number of bacteria placed in a growth medium, and then it over time shows how much bacteria is there. So which of the following functions best models the number of bacteria after T hours? So this up here is T, right? And okay, so what's your starting value? Okay, so at time 0, remember the starting value is always the value when when X, or in this case, excuse me, T is equal to 0. And at 0, that value is 1,000. So let's start this off. Actually, let's use n function of T because that's what they want us to use. N function of T is equal to 1,000 times, okay, let's put T up here because that's simply the change, right? Now, what is the growth factor? Now, the growth factor can be really simple sometimes because exponential models, they're not all percentage-wise. Sometimes they're just, oh, we're just going to multiply it by, 3, or we're going to multiply it by 4. So in order to find the growth factor, look at how much time has changed, and then look at how much the value has multiplied by, not how much it has added by, how much it has multiplied by, and you'll see a pattern. Because, okay, if you did addition, it by 3,000, And then if you did addition again, it would increase by 12,000. You might see a pattern there, but an easier pattern would be clearly it's multiplying by 4, right? And there you go. That's your growth factor. Every hour, it's multiplying by 4, and whatever the value your original population is being multiplied by, that's the answer. So yeah, there it is. So this is going to be the correct equation. Now, okay, uh, which answer is going to be correct? A is wrong, obviously. That's a linear equation. B, also wrong. That's a linear equation. C, n to the n of t is equal to 1,000 times 4 to the power of negative t. Okay, if you just use common sense, you'll kind of see that D is the correct answer. But remember how before I said that, one second. Okay, as I was saying, remember how I said before that T cannot be inside, but then now you're like, oh, what's the deal? T is on the inside here. Well, in this case, it's okay because this equation, if we expand it out, in reality, it's equal to 1,000 times 1.00 plus 3.00 to the power of t, because this is our original 100%. And actually, multiplying by 4 is considered an increase of 300%. So that equals 300%. And the thing is, you can just combine this into 4, right? At which point you get 1,000 times 4 to the power of t. And honestly, this is exactly the same thing as that. When both of those terms are combined, at that point, it doesn't matter. The t can be inside because the t is not directly interacting with the 1,000 anyway, so it's not going to affect anything if the t is inside or outside. It's only going to affect it if you have, your starting term. One second. If you have your starting term and then, okay, 1.00 plus, I'm going to represent the growth factor as y. It's only a problem if you have your t inside and attached to only one of the terms. That's an issue. Someone asked a question. Could I just plug in the values of t for each answer option? The answer is, well, yeah, you could do that, but that would take a really long time, especially if you start with the first option. I mean, think about it. The correct option is D, right? If you did the first what you said, then you would have to go through option 1, and then you'd have to go through A, you'd have to go through B, you have to go through C until you get to D, and at that point you would have wasted a whole lot of time plugging stuff in. It's better to learn exponential models. It's better to learn pretty much everything so that you have a method for doing things quickly. All right, here is some practice. This one's a little bit different, where instead of asking you guys to identify the correct one, all of the 3 out of the 4 ones are actually correct, and I'm asking you to find the one that is not correct. So I'm gonna give you guys 1.5 minutes starting now. All right, then everybody, 1.5 minutes are up. So let's come back and check out this question. Okay, so we have a table to the right representing a population of otters, and every half year the population triples. So I'm asking which of the following exponential function is incorrect. With the weird way I phrased this information and the weird way I presented it, there's a whole lot of stuff here that you could misinterpret, and there's a whole lot of ways that you can write an equation. For starting, I tried throwing you guys for a trick where initially you might think, oh, the growth factor or the multiplying factor is going to be 3, right? Because it's being multiplied by 3. Well, not exactly, because that is only half a year. If we're saying t represents the amount of years and we're thinking from the perspective, how much is it going to increase by 1 year? We have to look at it at an interval growth interval like this from 0 to 1 to 2. And how much is it really increasing by? It's really increasing by 9. Same thing goes for the second one, 900 to 8,100 multiplied by 9. So in reality, if we write our equation, y is equal to starting population as usual is going to be 100. So 100 times 9. Oh, wait, no. Yeah. Okay, 100 times 9 to the power of t. That's pretty much our simple equation. So, okay, we have this equation b. It's basically identical, so b cannot be the correct answer. What about a? Okay, well, a has the wrong growth factor, right? Wrong. Well, kind of wrong. You see how there's a different value up here to t? Well, 2t basically, it's doubling the time value. And actually, what happens is you can take this 2, you can simply apply that to the 3, and it's going to be equal to 100 times 9 to the power of t anyway. So that works. Yeah, that is true. Actually, when you're have an exponent, you can take parts of the exponent and apply it to the term that's getting exponentiated. You don't have to like take the t and apply it, even though you could because there's really no difference. Yeah, so the 2 is exponentiating the 3, and it basically comes out to the same equation. So A is going to be wrong. Okay, what about C? Okay, so let's talk about D first. D, you might think, oh, okay, well, this is probably the wrong answer. I mean, sorry, this is probably the right answer because there's a whole bunch of wrong things here. And yeah, you're right. D is the correct answer because it has a starting point, but it has an incorrect growth point, and it doesn't have a different value of t to account for that. Now, what about C? Some of you might have picked C because you thought immediately saw the weird starting point and thought, oh, okay, A needs to be the starting point needs to be 100, right? This one's 900, therefore C is wrong. If you pay attention, look what I put over here: t minus 1, where if you do t minus 1, then it's going to decrease your time value by 1. So this is actually that actually means that you have to account for that. And if you apply the -1 or the -1, it's going to come out and give you the same results. Let me show you what I mean. Okay, for example, if we're looking at 2 years, okay, we do 900 times 9, and then t is equal to 2, right? So 2 minus 1, this is going to be equal to 1. So then we have 900 times 9 is equal to 8,100, which is correct. And just take it from me, the same thing works for year 1, but now you're thinking, oh, what about year 0? This is going to be a perfect segue into our next section. We have 900 times 9, and then if we start at year 0, 0 minus 1 is going to be -1, right? So we have 900 to the times 9 to the power of -1. Well, you see, the thing about negative exponents is that negative exponents can create reciprocals, where if you have a to the power of -1, it's equal to 1 over a to the power of 1, power of positive 1. So this is actually equal to 900 times 1 over 9. And look at that. That cancels out to 100. Our starting population is 0. So yeah, now we're going to get into exponents using what we just learned. But before we do that, we do have a small mini quiz. I'm going to give you guys 2 minutes to do this. I think you can do it in 2 minutes starting now. All right, then, everybody. So another 2 minutes are up, a total of 4 minutes. Okay. So let's come back here. I'm not gonna lie, these are pretty difficult questions, so I don't blame you if maybe you didn't even get to the third question at all, or maybe you're still on the first one. It's okay. Let's go over it. A certain radioactive isotope has a half-life of 7.5 days. All right, some basic chemistry. Half-life is basically just the amount of time it takes for something to decay half of its value. So after 7.5 days, if you had like 100 grams, after 7.5 days would have passed, then it would have decayed to 50 grams, stuff like that. Okay. So scientist has a 100-gram sample of this isotope and he leaves it out for 30 days. Okay, so if it's a half-life, it's decreasing by half, right? It's being multiplied by a fraction. In other words, you could say, oh, it's being multiplied by 0.5. It should immediately give you a signal, oh, okay, this is an exponential system, right? Okay, so let's come up with our system. Y is equal to, you know what, actually, let's start out at the bottom since that's basically what the question is. Which of the following models represents the amount of sample left after n days? So, okay, what's your starting point? 100. Well, obviously, all the answer choices have 100 as a starting point. All right, then all right, yeah, what's the correct growth factor? Well, it's got to be 1/2, right? Because, well, it's decreasing by 50% or decreasing by half. All right. And then we have the days and days, but hold your horses. Remember how I said that half life is 7.5 days? So if you think about it, this represents the number of cycles that happens where, okay, if like, remember how in the previous questions there were time changes like, oh, years or days or something like that. So, like 1 year passes, that's like one cycle that goes on. In this case, 1 day is not one cycle because one cycle means one half-life, right? That's what we're basing this on. And one half-life is equal to 7.5 days. So then how much? So if n is like representing our cycle, then how many days? How are we supposed to convert days into one cycle? Well, simply divide by 7.5, and you'll see that 1 day is equal to n over 7.5, which is where all these wacky answers over here came from. It's going to be n over 7.5. So A be correct because we don't have that 7.5 thing. So is B. Initially, you might have thought, oh, D is the correct answer, right? But did you notice there's a negative over there? That negative sign? Remember what we said before, where if you have a negative exponent, you can turn it into a reciprocal where with a positive exponent. In this case, you can take the negative and apply it to the decay factor inside, and then that 1/2, if it's a reciprocal, it turns into 2/1, which is equal to 2, which is an increasing, not decreasing, which is not what we want. If we look at C, it has 2, right? And you thought, oh, well, that's, not the right one. But if you take the negative and you apply it to the 2, to the power of -1 is equal to 1 over 2 to the power of 1, which is equal to 1/2, which is the correct growth factor. So C is the correct answer. Oh, apparently I'm lagging a lot. I apologize for that. Currently it's raining and snowing a lot in my area, so Wi-Fi might not be the best. Hopefully my screen work should suffice. I'll try and be more detailed on the screen if I have to. And if there's a lot of unclear stuff, then at least we'll have the recording in the near future. Okay, yeah. So C is the correct answer, right? So if a scientist leaves the sample out for 30 days, around what percentage of the isotope will have degraded? So they're asking us how much has been lost. So, first thing you'd probably think is, oh, okay, well, let's solve the exponential system. Y is equal to 100 times 1/2 times, all right, remember how we have this n over 7.5 here. So in this case, we're going to do 30 divided by 7.5. And 30 divided by 7.5 is actually equal to 4. So this is equal to 100 times 1/2 to the power of 4, which, if you just pull your calculator, I can do it in my head. It's equal to 1 over 16. And then, okay, get your calculator out. What is 100 divided by 16? It's equal 6.25. Okay, so there's 6.25, and that means that there's 6.25 grams left after, well, that amount of days. And the thing is that, okay, well, 100 divided by 6.25, well, there's 6.25% of the sample left. So that means that there's 93.75% of the sample left. Let me start. 93.75% has decayed or degraded. But then you're thinking, oh, well, what's the right answer? 93.75 is not here. Well, remember that thing I said we have to choose the best answer? In this case, 95 is going to be the best answer because, well, yeah, it's 93.75 is closest to 95. Now, I'll be honest, on the actual ACT exam, it's not going to be as egregious as this, even though you might have answers that differ slightly. You're going to look at them and you're going to immediately think, oh, okay, this is obviously the correct answer. It's just off by like 0.1% or something. All right, this next one, a little bit more challenging. We had to split the equation into two parts. That probably already gave away the answer. Okay, in Antarctica is a population of seals with 700,000 members. Okay, that should immediately be a signal that the starting population is equal to 700,000. All right, one day the population is infected with a parasite that causes many of them to die. 40% of the population is immune, and the rest of the seals have their numbers decreased by 25% every day. Okay, so it's decreased by 25%, which means we know the decay factor is going to be 1.00 minus 0.25. It's going to be 0.75. That's what our decay factor is going to be. So if we write everything out, I'm just going to abbreviate 700, that's 700K to the power of what? Now, the thing is, there's an issue here where, okay, they're asking us what's the starting population, but the thing is that 40% of the population is immune, which means 40% of them are not going to die. So there's only a part of the population being affected by it. So we need to take the 40% and the 60%, the 40% that are not getting affected by it, and separate them. What is 40% of 700,000? It's 280, which means 420,000 seals. Y is equal to 420,000 times 0.75 to the power of D. And then we have our 280,000 seals that are doing just fine, right? They're not dying. So we just simply add that value onto there. That's therefore D is going to be the correct answer. A is wrong because it has the wrong change factor. B is wrong because it's considering that the entire population, you see how the decay factor is connected to the whole 700,000 population? That's incorrect because remember we said 40% of them are immune, so we can't apply decay to the entire population. It's wrong because the right population of sealing for the additional seals that are immune. That was a whole lot. Okay, exponential manipulation. This is honestly one that I really enjoy. Okay, remember how before I said if you have a to the power of -1, you can flip it into a reciprocal 1 over a. You can keep that 1 there to represent it's like a positive version of that exponent. Another way that this works is if you have a to the power of -2, it's equal to 1 over a to the power of +2, or a to the power of, just 2, right? So that was a very simple one. Now let's get into some more advanced ones. They're asking which of the following is equivalent to 1 over the square root of x to the power of n. Okay, one thing I want you guys to think about, you know how every mathematical operation, at least basic mathematical operation, has an opposite where, plus is opposite to subtraction, or plus is opposite to minus, and then multiplication is opposite to division? Well, actually, same thing goes for exponents, where the opposite of an exponent is a square root, where a represents the like either how much something's being exponentiated by, or how much or what factor something is being square rooted to. Now, so yeah, square roots are basically the opposite. Another way you can think of square roots is as an exponent themselves. Square roots are actually a type of exponent. Let me show you. We have a square root of x that's actually equal to x to the power of 1/2. Now you might be thinking, oh, I didn't know that. I thought exponents were like things that always increase stuff, right? Well, here's the rule. If you did x to the power 0, what is that equal to? That's equal to 1. And then anything above 0, well, okay, sorry. Anything, yeah, it's just equal to 1. And then you have x to the power of 1, which is just equal to x, right? So then what about the range in between 0 and 1? Well, at that point, it's going to be decreasing the value of x, whereas anything greater than 1 is going to be increasing the value of x. So square roots are like fractional exponents. And the cool part is that square roots can represent a whole bunch of things. Where, okay, you might have seen this before where you saw a little number above the indentation of your square root that represents the square root factor, or how hard something is being square rooted. If we had the cube root. This is called the cube root because it's done to the factor of 3, and well, 3 corresponds to cube, sort of, 2 corresponds to square. You can imagine that. A cube root of 27. Now, if you don't know in your head what this is equal to, well, think about it. 3 to the power of 3 is equal to 27. And this is essentially the opposite of that, where 27 under the root cube is equal to 3. So in other words, 27, this is equal to 27 to the power of 1/3. So, and you can imagine that, oh, well, 3 to the power of 3, 27 to the power of 1/3. You can see how it's kind of related like that. So, okay, I'm just going to clear everything. What we can do here is we can take the square root and convert it into an exponent. Because you notice how everything here has turned into fractions, has turned into exponents. There's nothing underneath. There's no square roots. In a lot of mathematical situations, you're going to want to convert everything to exponents. So in this case, this is equal to 1 over x to the power of 1/2 to the power of n. Now, another thing, remember what I said about reciprocals, where if you have a to the power of -1 is equal to 1 to the 1 over a. Well, the same thing can be true, where if you go in reverse, where if you have 1 over a, you can simply head back in the other direction, where you have a to the power of -1. Now, you notice here how all the option choices they don't have a fraction, they don't have x as a denominator, they have it as a numerator, that's a sign that we need to do exactly that, where we're going to go reverse. This exponent is going to go to the top. And in the process, here's the thing. When you are reciprocating exponents, the exponent value that they have, its sign changes. So if it was a positive, it changes to a negative. If it was a negative, it changes to a positive. So this is going to be equal to x to the power of negative 1/2 to the power of n. And here's another thing that you should know. X to the power of a, if you have x to the power of a, and then that term is enveloped by another exponent, guess what? You can multiply the exponents together. X to the power of a to the exponent of b is equal to x to the power represented in an example, but I'm not going to show that here. You can try it for yourself. In this case, we can simply combine those two values. And one second. Okay. And then we get x to the power of negative 1/2 n, or in other words, x to the power of negative n over 2. Therefore, our correct answer is going to be B. Okay, so I see that Zoom is telling me that my internet connection is unstable. Um, hmm. 1 second. I'm gonna just type in the chat so that everyone can hear me. But since my connection is unstable, I'll be turning my camera off. Okay, hopefully this should increase audio quality a little bit. Oh, I accidentally typed mom instead of my. Wonderful. Okay. So yeah, let's move on from this. And okay, this is the glorious exponent rules sheet that keep on switching for some reason. Cursor is hard to find. But yeah, this is the glorious exponent rules sheet that combines all the rules you need to know into one. And yeah, they're pretty much everything, bog standard. I suggest you take a picture of this or you screenshot this and keep it handy with you. I'll quickly go over these rules. Product rule is pretty simple. You have two exponents of similar types. You have 2 to the power of 2 times 2 to the power of 3, that's equal to 2 to the power of 5. The quotient rule, I'm going to use this as a fraction because fraction is the same thing as dividing, where, okay, if I have 5 to the power of 5 over 5 to the power of 3, then I take these two exponents over here and I subtract them. So I end up with 5 to the power of 2. And then power of a power rule, we just went over this. You multiply those powers. And then, this is another one. Power of a quotient, where, okay, if you have a fraction that is being exponentiated, you can apply the exponent to the numerator and the denominator. This is another important one, zero exponent rule. Literally anything to the power of 0 is equal to 1. 1,000,000 to the power of 0 is equal to 1. Yeah, don't ask me why that's the case. Just a mathematical law. Even I don't fully understand it. That's just what I know. Yeah, then we have the negative exponent rule, which is about reciprocals. And then the fractional exponent rule. This is a very interesting one that I want to go over, where remember how we have a square root, or sorry, not square root, or any root in particular that is kind of the same thing as an fractional exponent. So you can actually combine that with exponent rules where, okay, if you have a fractional exponent, such as a to the power of 3 over 2, this denominator represents the root, and this numerator represents the exponent, the increasing exponent. A to the power of 3 over 2 is equal to a to the power of 3, sorry, is equal to the square root of a to the power of 3. If it helps, you can imagine there being a 2 over here. Quick fun fact, this is equal to this. Your teachers, they just never showed you the 2 because in most math, you're always using a square root. You're not going above that. So they just never bothered to put the 2 there. But yeah, there's supposed to be a 2 there. And yeah, you can do fractional stuff like that. All right, so here is some fractional exponent rule stuff. There's a good amount of questions here. I think I'm going to give you guys 3 minutes to do it starting now. All right, everybody. 30 minutes are up, so let's come back and check out these problems. All right, first one is using the fractional rule. Okay, we have a negative exponent here, so there's 2 ways you can go about it. One is you can do the reciprocal trick, where if you give exponent, you can take to the numerator. So in this case, it could turn into 3 times 3 to the power of 5, which is equal to 3 to the power of 6. Another way you could do it is you could keep that fraction and you could do 3 over 3 to the power of -5. And remember, if there's no exponent, it's just exponent of 1, which is equal to 3 to the power of 1 minus -5. And the minus minus turn into a positive, so it's 3 to the power of 6, either way. The next one, remember, a square root is like the same thing as an exponential, sorry, a fractional exponent, where a square root is equal to the power of 1/2. So in this case, this is equal to x squared times, sorry, x to the power of 2 times 1/2. And then 2 times 1/2 is equal to 1, right? So it's just equal to x. Simple as that. This next one over here, y to the power of 5, under the square root of factor 4. Pretty simple, honestly. Remember, exponent is the numerator and this root is the denominator if you want to convert this into a fractional exponent. So it's y to the power of 5 over 4. All right, this next one, you might be a little bit confused because you're thinking, oh, look at this 4 over here. It's not the same base as 2, so how can we solve it? Well, actually, 4 is equal to 2 to the power of 2, right? So in this case, it's equal to 2 to the power of 6 times 2 to the power of 2. And this is going to be the exponential addition rule. If you have 2 bases that are the same and you're multiplying to each other, you add the exponents. The case is going to be 2 to the power of x plus 2. All right, these next ones, I tried throwing you for a little bit trick, and the answer is that they're both exactly the same, even though they have different parentheses. It's just in this one, you do the inner part first, where this turns into 4 to the power of 2, which is equal to 16. Pretty simple. This one, you know the rule PEM where you have to do parentheses and exponents first? Well, that applies doubly here, where you have to do the exponent of the exponent first, and then you do that one next. But in this case, they end up at the same thing, where this turns into 2 to the power of 4, and then that's also equal to 16. So yeah, that's that. Okay, this next question, 10 over 3. Okay, simple fractional rule. 10 to the power of 3 minus 1 Imagine there's a 1 there. That's equal to 10 to the power of 2, simple as that. Okay. So that's pretty much exponential manipulation in a nutshell. Okay, before we move on to the next part, I want to head back. This is a mini quiz that should review quadratic formula stuff, which we learned last session, and also takes a little bit into account what we are learning now. Actually, wait, no, never mind. I changed my mind. There's still a little bit of stuff we have to know. So let's continue onwards. Is it located anywhere here? Okay, it looks like it's not. Okay. So, first question. What are the possible solutions to the given equation? Okay, there's a little bit weird, something weird going on here. We have one half of the equation being under the influence of a square root. Now, here's the thing. Square roots, they're kind of annoying because they're really hard to work with. You can't just ignore them. So what you need to do is, common sense might think, oh, why don't we just square the whole thing? And you're right, you can actually do that. If we square the whole thing, we get x minus 12 squared is equal to the, oh wait, not the power, it's equal to x plus 44. And if we unfurl the left side, we get x squared minus 24x plus 144, which is equal to x plus 44. And then, okay, we can simply take these and simplify them and into x squared. And let me make that completely in the black area. X squared minus 25x, and then minus 44. Yeah, so minus 100 is equal to 0. And then in this case, you simply, factor it out. In my case, I can factor it out pretty easily. It's something that comes with practice. You'll do x minus 20 times x minus 5, which is equal to 0. All right. And then you get x is equal to 5 comma 20. So therefore, oh, wait, no, there's an issue here. You see, the problem is that although we have two seemingly good answers, which is going to be 5 and D, the thing is that since we squared an entire equation, the thing about squaring is just a general rule of thumb. Sorry, I'll write exponentiating or rooting equations can create extraneous answers. An extraneous answer is basically an answer that seems like it's correct, but it's not actually correct. It doesn't realistically work. I'll show you what I mean. All right, let's take one of our answers, supposed answers, 20. If we plug that into the original equation, what are we going to get? Okay, 20 minus 12 is equal to the square root of 20 plus 44. 8 equals 8. That works, right? Now, what if we take the 5? If we do 5, then we get 5 minus 12 is equal to the square root of, what is that? All right, 5 plus 44, this is equal to 49. And square root of 49, right? But then on this side, 5 minus 12, what's that? We get negative 7 is equal to 7, which is not right. You see the problem here? 5 is not an actual answer because even though it seems like it works algebraically, it's not going to work if we apply it realistically. So in this case, the only correct option is going to be B. 20. Now, some people said, could you just plug those numbers in? Yeah, you could plug those numbers in. I'm sure that it might take a little bit extra time, or in this case, since it's a lengthy process and some people might not be good at factoring things quickly, it could be quicker for you to plug things in. So yeah. Oh, it seems we have some questions. Sanvi, yes. Unfortunately, I cannot hear you. Sorry. Unfortunately, I have to move on. Avanish, you have a question?
Yeah, actually, the square root of 49 can be plus or minus 7, right?
The square root of 49.
Yeah, it can.
Um, the square root of 49 can be plus or minus 7. No, actually. It is impossible to use roots on something that that is impossible. You can't actually square root something negative because think about it. If you're doing a square root, then the final answer it has to be reversible, right? Where if you do the square of that answer, then what you originally got back. For example, if you do the square root of 4, it's equal to 2, right? Now think
Mhm.
about it. If you did the square root of -4, okay, let's just say, okay, if it's equal to 2, well, the problem is if we try and go back, or if we do 2 to the power of 2, that's equal to 4. It's not
N-
equal to -4. But then you're thinking, oh, why don't we do -2? -2 squared, it's again equal to 4, which is not, I forgot to put the not sign there, not equal to -4. So it's actually impossible to square root a negative number.
No, no, no. No, what I'm saying is the square root of 49 can give plus or minus 7, right?
The square root of 49 can give plus or minus 7.
Because 7 square and minus 7 square will eventually give 49.
Well, yes, you are right that if you square -7 or 7 either way, it will end up at 49. Um, wait, actually, yeah, now that I think about it, that oh yeah, that is actually a derivative. That is actually a result of the whole squaring process. Yeah, that is another way you could look at it. Oh, but you're thinking purely algebraically, right? Where, yes, you are correct. The square root of 49, it could be equal to, 7 or -7, but that's not going to work realistically here because you see, we're just plugging in the numbers that we got from the algebraic equation, right? And you see, in reality, um, square roots you see, square roots, that only works when you're square rooting an equation or something. If you're square rooting a number, it's actually not possible to get a negative result. That's just not how it works. I understand where you're coming from, but that's like a different advanced thing.
Okay, so it means like whenever you square root a number, like no, because like most of the time which I've learned, like you get plus or minus of a number which you have square rooted.
Yeah, that is true algebraically once again, but if you look
It's fine. I'll just
logically,
like
yeah,
after the class I'll ask you.
sure, no problem. Yeah, let's continue on. Okay, what about the next problem? Okay, which one should I do? Okay. All right, let's move on to the one directly to the right. What are the possible solutions to the given equation? 2x minus 3 to the power of 3 is equal to -27. Now, okay, first thing you might think of, okay, why don't we do a cube root? Instead of an exponent, we're going to do a root where we try to get rid of the exponent. So in this case, we end up with 2x minus 3, which is equal to, okay, now remember how I said you can't square root a negative number? Well, the thing is that that depends on whether or not the root factor is odd or negative, because square root, it's even, right? But a cube root, it's odd. And the thing is that if you think about it, it works in the reverse direction, where if you have a cube root of -27, it's actually going to be equal to -3. Because think about it, if you do the reverse, -3 to the power of 3, since there's three negatives, it's going to be negative times negative times negative. Two of the negatives will cancel out. I'll represent it. You have three negatives. These two negatives can cancel out into a positive, but you still have one negative. So the overall answer is going to be negative. So you end up with negative 27. So it works in this case. So 2x minus 3 is equal to negative 3. And then, yeah, you simply solve for this equation. Plus 3 plus 3, 2x is equal to 0, and then you get x is equal to 0. So then, okay, the correct answer should be A, but just in case, let's check out the other options to see what we get. Okay, so if we do A is equal to 0, we can plug it in directly into the original equation and we'll see that it works out. Now, what about 6? Why did they put that there? Well, let's see what happens if we put 6. If we put 6, then, oh, well, you simply get 2 times 6, 12, which is 12. 12 minus 3, it's 9 to the power of 3. It's not really going to work out. So yeah, A is just the correct answer. Simple as that. Okay. Oh yeah, this one over here, I'm just going to rewrite that. Cube root of x is equal to 2. Now, okay, what are the possible solutions to the given equation? If you cube something, right? Yeah, if you cube something, then the same thing works in reverse, where you can actually carry over the negative and positive signs. So we end up with x is equal to 8. Simple as that. The correct answer is going to be B. Now, just in case if you wanted to check whether or not a -8 works, if you do the cube root of -8, that's going to be equal to -2, which is obviously not equal to 2. So yeah, that's why -8 won't work here. So remember this odd exponents are situations where you can carry the signs over, but then positive situations are ones where you cannot really carry over the signs. Okay, this one over here. Uh, uh, oh yeah, Avnish, I think you actually do have a good point. Good point. Yes. Um, yeah. So, okay, in this case, you're gonna see what me and Avanish were just talking about, where when you deal with even exponents, you're gonna have to do positive and minus versions. In this case, let's root the whole thing by a factor of 4. We get x minus 8, and then, oh, well, what's 16 to the root of 4? Well, might be a little bit difficult to think out of nowhere, but if you think in a reverse manner, okay, well, let's start at the beginning, small numbers. What's 1 to the power of 4? That's 1. What's 2 to the power of 4? Oh, that's 16. So this is just the reverse. So therefore, it's equal to 2, but here's the thing. You see, remember we said about extraneous solutions where it can sometimes create new answers? Well, yeah, that's what's happening here, where new answers are being created, or yeah. Uh, One second. Yeah. Anyway, as I was saying, you see, if you do -2 to the power of 4, it's equal to 16. It's equal to the same thing, right? So you have to consider the negative version. And in that case, you have to create two equations where x minus 8 is equal to 2. and then x minus 8 is equal positive 2. So what answers do we have here? This is going to be one where x is equal to 10. And this is, oh, wait, no. I still made a mistake. Oh, yeah, let's just pretend that was negative 2. All right, if we add 8 to both sides, we're going to get x is equal to 6. And then here, plus 8, we're going to get x is equal to 10. And you can plug both of those values into the equation. They're both going to work. Oh, I unfortunately forgot to write a 1 there. But in this case, D is going to be the correct answer. Um, okay, regarding the first question, yeah, no, there might be some debate up for that. I might post a follow-up to that later, so there's no need to ask me about it. I'll look into that myself because I am intrigued myself. Okay, so now I think we're ready for that mini quiz from before. Yeah, so here's your mini quiz. I'm gonna give you guys 5 minutes to do this starting now. All right, everybody, 5 minutes are up, so let's come back and check out these answers. Okay, for the quadratic equations, I'm not going to write out the whole process. I'm just going to give you the correct A, B, and C values that you should have used. You're gonna have to manipulate the equation a little bit for some of them, like the first one, 5r squared, that should be 5r squared minus 80. In this case, A will be equal to 5, B will be equal to 0, and C will be equal to negative 80. For the next one, simply move that 10 over there, 2m squared minus 7m. Minus 3 is equal to 0, therefore A is equal to 2, B is equal to negative 7, C is equal to negative 3, and yeah, same on, it's basically the same thing for the third question and the fourth question. Honestly, we can just move on to the next ones that are much more interesting. Okay, if x is not equal to 0, what is the product of the solutions over here? So, okay, we're going to do a little bit of factoring. If you notice, there's an x common through every term, so we can factor out an x. And we get x squared minus 6x minus 27, which is equal to 0, and that factors out to x minus 9 times x plus 3, which is 0. And then we get x is equal to 0, negative 3, and 9. And then, oh, the product of the solutions, it's going to be equal to 0, right? Well, no, they said x is not equal to 0. So we have to ignore this. And then we just are left with negative 3 and 9. Therefore, B is going to be the correct answer. Yes, Avanish, you have a question?
Well, I don't know, like this may be useful, but like for finding the product of the solutions, there's a formula called C by A. That means dividing the C value by the A value.
Yeah, I have heard of that. Yeah, you could use that. Sometimes it won't always work though if you have multiple factors. If you have a equation that is not an quadratic x squared equation, sometimes it might give you just a linear equation, or sometimes it might give you a cubic equation. That what you just said might work for a quadratic equation. But yeah, I might look into that. Maybe I'll check it out and give a lesson on that next session. Thank you. Okay, for our next question, 5x minus 8 is equal to 16. All right, we'll just root the whole thing to a factor of 4. And remember, since we're rooting by an even number, we have to do the plus or minus split. We end up with 5x minus 8 is equal to 2, and then 5x minus 8 is equal to negative 2. Okay, so the two solutions we end up with are x is equal to 2, and we also end up with x is equal to 6 over 5. So the sum of these solutions, just some fractional addition you have to do. The correct option is going to be D. Ooh, okay. Now, okay, what about the next one? Which of the following is equivalent to that x squared over x to the power of negative 1/2? All right, just you gotta use some simple rules here. Since it's a negative, there's two ways you can do it. What I like to do is I like to get rid of all the negative exponents. So bring this to the numerator. So x squared times x to the power of 1/2, which is going to be equal to x to the power of 5 over 2. So A is going to be the correct answer. All right. It was a lot of stuff to do, but relatively simple quiz, not that convoluted. Unlike the next thing, which is enormously convoluted, solving rational equations. So sometimes it might give you this abomination of an equation where you have a whole lot of variables on the denominator. So this is really hard to work with. The solution, literally multiply the whole equation by every single term. I'm not joking. This is how you actually do it. Yes, even the parts that don't have the variable. So let's just think about it. If we multiply the whole equation by all three of these terms, then what are we going to get? For the first term, we have our numerator, 3, right? So I'm going to use a different color for each one. The T1 over here, pink, it's going to get canceled out, right? So we are left with T plus 3 and 4 as on top as the numerator. So T plus 3 times 4, that's going to be the first term. And this is equal to, we have uh we have 2 as the numerator. 2 times what? Okay. So okay, multicolored T. So we have T plus 1, T plus 3. The T plus 3 will cancel out with the T plus 3 at the bottom. So we are left with T plus 1 times 4. And then plus, okay, in this case, the 4 cancels out with the 4. So we are left with T plus 1 times T plus 3. And then, yes, you do need to expand the whole thing. So let's do that. First term is going to come out to 12t, it's 36. And then the second term, 8t plus 8 plus t squared plus 4t plus 4. And then now we have to combine the whole darn thing. Okay, so if we combine everything, let's go in this direction. So subtract 12 from the whole equation, sorry, 12t, and then subtract 36 from the whole equation. If we simplify the right side over here, we'll end up with t squared plus 12t plus, what is that over there? Um, 4 plus, oh, did I forget to write some? No, that was 4t. All right, yeah, 4t, 8t. Sorry, the t's look a lot like pluses, so I got a little bit confused myself there. But yeah, 8 plus 4, yeah, plus 12. And if you notice here, this 12 will cancel out with this 12. And we're subtracting from 36, right? So we end up with 0 is equal to t squared minus, oh wait, I hope I didn't make a mistake. Seems a little bit awkward. 2 times 4 times t to the 1, t plus 1, t plus 3. Hmm. Oh, shouldn't the very last number be 4 on the last side? Let me check that. Oh, yep. Think you are, in fact, right. If that is 4, then oh, yeah, that's my supposed to be -4, I believe, or not. Apologies. Let me just Sanvi, do you have a question? Unfortunately, I can't hear you, sorry. Yukti, you have a question?
Yeah, I think the last number, I know it's erased now, but the last number I think should have been 3 because it's like 3 times 1.
Oh, yeah, that was my bad, extremely. Honestly, I'd like to really apologize, guys. Yeah, today was just a really long day, 2 exams for me, so, yeah, apologies if I'm a little bit foggy today. But yeah, that should have been a 3, and then this is gonna be 11 minus 25, and yeah, we're gonna end up with a very nice number of 25. 0 is equal to t squared minus 25, which is going to be equal to t minus 5 times t plus 5. And then, okay, they're going to say, what is the value of t? They say t has to be greater than 0, right? So even though we say t is equal to -5 and 5, since -5 is less than 0, we exclude that, and 5 is the correct answer. Now, although I did make a mistake before, I think we can turn this into a valuable teaching lesson. You remember how when I looked at this 0 is equal to t squared minus equation, and remember how this before was actually 4, and then we got the wrong answer of t squared minus 24. When encountering a problem like this, there should be alarm bells going off in your head because a situation where you have an equation like a squared minus b squared is equal to 0, these both have to be perfect squares. Now, in this case, t squared, it's a square. It's always going to be a square. We know that, right? But then you're telling me 24 is equal to b squared? Well, 24 is not a perfect square. It's not a squarable number, easily squarable number, right? So that should be immediately a signal that something is wrong. And on the SAT, it can be very important to recognize when you're doing something wrong so that you don't speed ahead. Okay. Oh, so advanced systems of equations. It's I said advanced, but honestly, it doesn't have to be that advanced. Okay, so I'll show you guys what I mean. In this case, we have two systems, right? Y is equal to 2x plus 2, y is equal to x squared plus 6x plus 5. There's two simple ways you could solve them. Okay, wait, just to make sure that I'm on the, okay, yeah, I'm on the right track. So yeah, this is relatively easy to solve, but I'm going to show you guys another way to solve it where you create your own variables. You notice how this is factorable into y is equal to 2 times x plus 1. And then look down here. This is factorable into y is equal to x plus 1 times x plus 5. Now here's the thing. One way you can do it is you can take x plus 1. If you notice that there's a common algebraic term in between these, you can take the algebraic term and set it equal to a variable, like say x plus 1 is equal to a. And then you can replace the x plus 1 with a in your equations. So you have y is equal to 2a, and y is equal to a times 2x plus 5. Oh, sorry, not 2x. Where did that 2 come from? After exam brain, I'm telling you guys. And yep, pretty simple, honestly. And you can substitute these things in for each other. And basically, what I'm trying to say is you have to look at the big picture and imagine what could happen if you take algebraic terms and you turn them into variables. And I'm going to show that in the next slide right here. You see this monstrosity of an equation. Now, typically, you might think, oh, why don't we just expand this whole thing? And yeah, you could expand the whole thing, but that might take a lot of time. So another thing you can do is do the thing I just told you, where you condense an algebraic equation into something simpler. So here we have, let's simplify this to y is equal to negative 3x minus 3. Okay, that wasn't really simplifying, but you know what I mean. Excuse me. We can factor this into negative 3 times x plus 1. Now, if you notice here, x plus 1 is a common algebraic term here, and you'll see that x plus 1 is getting squared, so which innately makes the whole thing a little bit more complicated. It can be really simple to take x plus 1 and convert that into a big fat variable. Let's say x plus 1 is equal to a. Immediately, look at how simple everything becomes. Y is equal to negative 3a. This corresponds to the first equation. And then y is equal to, this corresponds to the second equation. Y is equal to a squared minus 4a minus 6. And that looks a lot easier to solve, in my opinion. There's a whole bunch of ways that you can solve this. I'll show you guys one method I think we haven't gone over, which is substitution, where you just simply set these two equal to each other right out of the gate, and you do negative 3a is equal to a squared minus 4a minus 6. Oh, wait, actually, no. We already did do that substitution as something else, but we basically end up with 0 is equal to a squared, okay, minus a minus 6, and then we can factor this into a minus 3 times a plus 2, and then we end up with two solutions or half solutions. A is equal to negative 2 and 3. Now, remember we said a is equal to x plus 1. Now we have to still substitute that in here. X plus 1 is equal to negative 2 comma 3. So then we have two solutions. X is equal to negative 3 and x is equal to 2. And they ask, now keep in mind, we're still not done. Is that if xy is a solution of the systems above and y is greater than 0, what is the value of y? We only found the x variables, now we have to find the y values. Okay, simple enough. Let's just find the situations where the y variable is greater. So, okay, let's take when x is equal to negative 3, let's plug that into the first equation. What do we get? We get y is equal 6. And then if we take x is equal to 2 and plug that into the first equation, we get negative 9, I believe. Oh, wait, no. The top equation, x is equal to negative, when you say x is equal to negative 3, that should be, oh, wait, no. I did that right, that's for sure. Okay. Yeah, no, everything is okay. So yeah, y is equal to negative 9. This is less than 0, right? So therefore, we can't use this solution. So we are stuck with this one, x is equal to negative 3 and y is equal to 6. Avanish, you have a question?
Yeah, actually. Oh wait, never mind.
Okay, no worries. All right, so here is some practice that I made for you guys. This one is a little bit complicated because I will say you do have to use the skill from before to make it easier, where you use a common term, but notice how the common term, you have to modify it a little bit. I'll give you guys 3 minutes to solve this starting now. All right, everybody, 3 minutes are up, so let's come back and check out this question. Okay, so first thing right off the bat, you should have recognized that 3x plus 1 is going to be the common algebraic term, so we can set that equal to something like a. We end up with y is equal to a for the first equation. Second equation is where it gets a little bit weird. So clearly, 6x plus 2 is just 2 times 3x plus 1, which is equal, in this case, to 2a, right? What I'm afraid some of you guys might have done is you probably did y is equal to 2a squared for the first term. That's not right, because you see how this is in parentheses over there? Oh, wait. Never mind. Yeah, you see how the 6x plus 2 is in parentheses and it's being squared? So if you're doing 2 times 3x plus 1, this whole thing is being squared. This 2 applies to the 2 coefficient over there. So in reality, the correct coefficient is 4. And you can also see it reflected another way, where 2 times 3x plus 1 is equal to 2a. So this technically turns into 2a squared, which is equal to 4a squared. Then it's smooth sailing from there on. 5a plus 1, you simply set them equal to each other, and you end up with 4a squared plus 4a plus 1, which is equal to 0. And then we end up with, if you factor this, you should recognize it's one of those easily factorable ones where it's 0 is equal to 2a plus 1. Okay. And then 2a plus 1 is equal to 0. And then a is equal to negative 1/2. And then we simply take our value, 3x plus 1 is equal to a. We bring that over here. So, oh, wait, actually, no, we don't have to do that. Remember what we said, where the question is, what is the y value of the solution of the system? Although yes, we do need to find x to find y. Remember, we just turned this x term into a big fat variable, right? So this is the same thing as y is equal to a. Well, if we know what a is, we can use the a value to find the y value. So simply, y is equal to negative 1/2. Therefore, a is the correct answer. If you find that it helps you, you can convert it back to X, like, for like logic's sake, if you like to see that, but it'll be faster to do it this way. Phew, okay, now we're gonna do some learning. Okay, so when it comes to functions, there's a couple of definitions you need to know. This should be pretty basic. First of all, is going to be intercepts, which is simply the points where the function is intersecting with the axis, x or y axis, whatever. And then there's going to be domain. So domain is the range of x values for which the function exists. So basically, everything where all the x values where you will see the function. And then range is, well, the range of y values for which f of x exists. Now, this seems pretty random, but I'll explain why it's important. Ignore that. I'll get to that later, and that one's wrong anyway. Okay, you see how this arrow over here, you see that the y values, they all go up, but they don't go beyond this. They don't go below 0. So the domain, it sorry, the range, my bad. The range is going to be from 0 to infinity. And then, okay. Oh, actually, my bad. I think I mixed up the symbols. Okay, I'm going to use brackets instead. I'll explain why these brackets are important in 1 second. 1 bit. Okay, yeah. So there is a difference between square bracket and parenthesis. Square bracket means that the point is included, and then parenthesis means that the point is not included. So what does that mean? So you see how we have a square bracket for 0? Square bracket means it includes 0, which means that the y value, it's reaching 0, it's touching 0. And then we have this parenthesis over here. So although it's going towards infinity, it's not actually going to reach infinity. This is just a general rule for infinity. When you're representing infinity, you use a parenthesis, not a bracket, because yeah, it's just infinity is something unreachable. Okay, now what about domain? Domain is the range of x values. You see how the domain, it kind of stops at 1, but if you look closely, it's going upwards and upwards super duper close to 1, but it's not actually touching 1. And even if it goes all the way to infinity in terms of y value, it's never going to touch -1. It's never going to touch -1. So the way to write the domain is going to be parenthesis -1 infinity, because it is going in the right direction, infinity. So we're going to put both parentheses there. And yeah, once again, we put parentheses for -1 because although the range is extremely close to -1, you can think of it as a stopping point. It's never going to touch -1. Okay, some more definitions you'll see on the ACT. Maximum and minimum values, these are simply the lowest and highest points on a graph. If you have a parabola, that's the max. If you have a negative another parabola, that's the minimum. Okay, and the next important thing is graph behavior. So when they say that when a question says the graph is increasing or decreasing, this is talking about whether or not the graph is moving upwards or downwards as it's progressing. What I mean by this is, okay, if you have a parabola over here, if you looked at this point over there, let me use red. If you looked at this point over here, even though the point is above 0, you see how it's the whole function is heading downwards? You would say that at that point, the graph is decreasing. Meanwhile, at this point over here, even though it's below 0, it's going in an upwards direction, right? So you would say it's increasing at that location. Another important thing is end behavior, where you identify where the graph is going to end up as it reaches positive or negative infinity. So let's make another graph. Let's have a cubic function like this. Okay. So if we, in terms of x value, go all the way to infinity in the right direction, is the y value going to be positive infinity, or is it going to be negative infinity? Well, clearly the arrow it's going up, right? So when x is increasing in the positive direction towards infinity, y is increasing in the direction of positive infinity as well. Now, what about the other side? As x is approaching negative infinity represents how you're going in the left direction. You see how the graph is heading downwards and there's nothing changing it? That means as x is approaching negative infinity, y is approaching negative infinity as well. And another concept you need to be aware of is transformation, which is simply modifying and shifting a graph to have different appearances. This can mean a whole lot of different things. Like a simple transformation is simply taking a line and moving it up by increasing the y-intercept or something like that. We'll go deeper into transformations if we have to. For now, I don't believe we have to. Okay, yeah. So when it comes to quadratics are a super duper important part of math in general and the ACT especially. There's a couple of different types of quadratics. So these are forms of quadratics where every single one of the equations you see here is a quadratic. They're just written differently and they have different purposes. The standard form, ax squared plus bx plus c, the good old, it's handy, it's recognizable, but the problem with it is that it doesn't really tell you anything, tells nothing useful except for y-intercept. Okay, now the intercept form over here, where you have x minus p times x minus q, this represents, it tells you the x-intercepts of the quadratic super easily because you can simply take these two terms. If when you set the equation and get to equal to 0, you simply take those two terms and you can set each of them equal to 0, and then you found your solutions. Really easy. So yeah, I already wrote that there. The next one, the vertex form, it tells you what the vertex of the quadratic is. Just a reminder, in a quadratic equation, the vertex is the highest point or the lowest point of a quadratic, okay? And I'll explain what each of the variables in the vertex form mean. So we have a times x minus h squared. X minus h, this x, if we set x minus h is equal to 0, then the x coordinate of the of the vertex is equal to h. And then k in this case is going to be the y value for the intercept. Maybe it's better if I give an example. If we had an equation such as y is equal to 2 times x plus, oh wait, small mistake there. X is not equal to h, it's equal to negative h. But yeah, as I was saying, x plus h, not h, x plus 2 squared plus 5. What we do is we take the x plus 2, set that equal to 0, and we get x is equal to negative 2. That's going to be our x coordinate for the vertex. And then we simply take the plus 5. It's going to be our y value for the coordinate vertex. And then our vertex, we simply know is going to be negative 2 comma 5. Honestly, pretty easy to determine the vertex. Yeah, same thing, these two equations, they give really useful information. The crazy thing is that all these three quadratic equations are actually the same exact equation, just written differently. From the intercept, the intercept is going to be 1 and it's going to be 3. From the vertex form, you know that, the vertex is going to be at 2 comma negative 1. So that's why different quadratic forms are really useful. So, for example, let's take this question. I'm going to give you guys just 1 minute, and I want you to think about the question. and have an answer in your head, starting now. All right, everybody. Should have had a minute to think, so let's check this question out. The graph of which of the following functions of the xy plane has x-intercepts at -4 and 5. First, you have to identify which equation is going to help you. This equation, these two equations over here are in vertex form, so they're likely not going to be helpful. Let's take a look at the first two forms since they're in vertex form. You set these two equal to 0, those two parts equal to 0. For B, your x-intercepts are going to be at 4 and -5. That's not what we want. And therefore, A is going to be the correct answer because if you do the math, it's going to give you intercepts at -4 and 5. Okay, let's move on. I think the next question should be a little bit more applicable. Okay, interpreting complex equations in context. So this is a type of word problem where they tell you about a function that exists, but they don't give you any information on it except for how it's used in real life. For example, first question. For a certain reservoir, the function f gives the water level f of n to the nearest whole percent of capacity on the nth day of 2016. Which of the following is the best interpretation of f of 37 is equal to 70? So, okay, the nth day of 2016. So the nth day corresponds to the input, right? I mean, the input is literally n, so we know that nth day represents input. So n, that corresponds to 37th day. What does the y value mean? They asked for a certain reservoir, the function, it gives the water level to the nearest whole percent of capacity. So it gives a percentage that tells us the capacity of a reservoir. So what does 70 mean? 70 represents 70% capacity. So which answer best matches this interpretation? A, water level at the reservoir was 37% capacity for 70 days. Okay, well, that doesn't make sense. That's the wrong numbers, right? B, 70% capacity, 37 days. Okay, might be a good answer. Let's check out the other ones. B has the right numbers, but the other ones might make a little bit more sense in context. C, on the 37th day. Okay, on the 37th day. This one is more correct or makes more sense because remember how it says nth day? They're not talking about total number of days, they're talking about a specific day itself, a specific date. On the 37th day, the water level of the reservoir was at 70% capacity. C best matches our answer. Okay, now what about the next question? Oh, whoops, my bad. Okay, if an object M is moving at a speed V, kinetic energy is given by Ke is equal to half times m times v squared. If the mass of an object is halved and speed is doubled, how does the kinetic energy change? Okay, you might be a little bit confused because you're like, okay, well, how am I supposed to know? Like, they didn't give me a value of m or v. Well, okay, well, here's the thing. There's two ways. You can either make your own values up, or you can simply make variables or metaphorical variables. For example, they say, if the mass of the object is halved, okay, if we have m, which represents full mass, then m over 2 represents half mass, right? And then if we have v representing velocity, then 2v represents double velocity. Now, guess what? We simply take these values and we replace them into the equation where we get 1/2 times m over 2 times 2v squared. And guess what? If you simplify everything out, it comes out to mv squared. And mv squared is exactly double that of half mv squared. So if you half the mass and double the speed, your final answer is going to come out to double the answer of the original So therefore, which answer makes the most sense? A, that's going to be wrong. It's lowering. B, it's definitely changing. C, yeah, correct answer. It is doubled. So, okay, I don't think we'll have enough time to do these questions. So I think we'll end the class here. Actually, we'll do these practice problems next time. As usual, I'll stay back and answer any questions you guys have. But for now, yeah, class is dismissed. It was wonderful having you all here, and I'll see you on Friday.